I think we have done this line integral, surface integral, some basic part already, isn't it? So still let me take what you call line integral. Line integral of a vector field, okay? We don't quote that one, but whenever we say line integral, we are talking about line integral of a vector field only. Is that okay? So we have, let us choose the, what you call, so our origin here, okay? X-axis, Y-axis, Z-axis, okay? Let me choose a point A in space, okay? Point A means, again, let me define a position vector of this point, okay? A vector. Any point in space is defined by its position vector. Speak out. Any point in space is defined by its position vector. So let me define one more point in space. Let me call it as what you call B, okay? So position vector is B, okay? Let me call this one as B. Now I will go from A to B. I will go from A to B. So again, in some particular path, there are infinitely many paths that is linking A to B, isn't it? Infinitely many paths. Let me choose one of those paths, okay? We call this as point A, point B. Is that okay? So actually, so if I remove this one, is that okay for you? Let me remove this what do you call this position vector. Okay, what I do here is I'm going to write this one as A vector, this one as B vector. That means I am quoting its position vector here. Okay, is that okay? Speak out. I'll say this is point A, that means it is represented by a position vector A. Point B, that is represented by a position vector B, okay? Now what we do is, again, we have a vector field in space, okay? We have a vector field, okay? So that is, so throughout this space, okay? Then as I told yesterday, isn't it? What we do is, we are going to divide, what you call this path into infinitesimal displacement vector, isn't it? Infinitesimal displacement vector, and at each and every point on this path, what we do is, so this is a vector field V, okay? It is throughout the space. So at each and every point on that path, we take V dot dl vector, okay? Dot product with a vector field at that point and displacement, infinitesimal displacement vector, okay? We take that product, okay? So then we integrate and we write that one from A to B. I think I did already explain this one, isn't it? Suppose if you take it here, again, so your vector field may be in this direction, your dl vector may be in this direction. If you take it here, your vector field is in this direction, dl vector is in this direction. At each and every point on that path, you take this dot product, okay? dl is infinitesimal. You can define dl vector from a point to the neighboring point. That neighboring point is arbitrarily close to that point. Infinitesimal displacement vector, okay? So that's why you can define this dot product at each and every point on that line, okay? And you can take the integral of these dot products. Dot product is a scalar, okay? You are adding that one. Is that okay? Now, if B coincides with A, am I right? If I start from here, if I go around some what you call region, and if I come back to the same point, okay, then we call it as closed line integral or closed path integral, isn't it? That closed path integral have got symbol closed path integral of V bar dot dl bar, okay? Now, whenever you write this path integral, either open, can I call it as open path integral, closed path integral, okay? Whenever you, what you call, define this one, okay? Whenever you define these integrals, okay, this path should be well defined, okay? Unless you define the path, where you take that path integral, isn't it? That's a question that will arise usually, okay? But there are some special class of vector field, okay? There are some special class of vector field where this path integral is independent of the path taken. In the most general case, okay, this path integral is depending on the path chosen from A to B. Suppose if you choose some other path, is that okay? it may be different. For the most general vector field, okay, in the ordinary case, this path integral depends on what you call path chosen. Is that okay? There are infinitely many ways of going from A to B. There are infinitely many paths, okay? And usually ordinary vector field in the most general case. So again, this path integral will depend on the path chosen, which path you have taken. Okay? If it is depending on the path chosen, then you have to define path, isn't it? If you just write this integral from A to B, it will be quite meaningless, isn't it? Which path I have to take from A to B to do this line integral, isn't it? That's a question. But there are some special class of vector field where this path integral independent of the path chosen. Is that okay? Whatever the path you take from A to B, that path integral remains the same. That depends only on this initial point and end point. Is that okay? So we call that as a conservative field actually. In that case, for that kind of vector field, so this closed integral will be 0 actually. We can prove that. So that's a special class of vector field. We need to study that one. Okay? Because later we will get that kind of vector field only. Our electrostatic field, okay? Electric field is such a vector field whose line integral is independent of the path chosen. Yeah, so quickly, any question? But in the most general case, this is usually path dependent, okay? That's why whenever you define a vector field, okay, so whenever you define a path integral, usually you need to specify what is the path chosen, okay? Whether it is a closed line integral or open line integral, you have to choose that one. But for a special class of vector field, whatever I told, whose so path integral is independent of the path chosen, isn't it? If path integral is independent of the path chosen, then you don't have to specify the path at all, isn't it? You can specify only initial and final point, okay? So that's a special class of vector field, okay? We need to study that. Yeah, speak out.
Sir, there's a line integral for conservative field is 0, sir.
The closed line integral is 0, okay? For the special vector field, whatever I told, whose path integral is independent of the path chosen, okay? So for those vector field, closed line integral will be 0. We shall see that one. Is that okay?
For conservative field, sir, closed line integral will be 0.
Yes, for conservative field, closed line integral is 0. Whatever the closed path you take, okay? Whatever the closed path you take, closed line integral will be 0 for conservative field.
It is 0 in the entire field, sir.
It is?
Closed line integral. Sir, it is 0 in entire field, entire conservative.
No, wherever this closed path you take. If the field is conservative field, conservative means, again, mathematically conservative field is defined from this one only, okay? It is a vector field whose line integral is independent of the path chosen. It depends only on the endpoints. Mathematically, conservative field defined like this only, okay? But again, wherever you take, whatever the 2 point you choose, okay? That special class of vector field, okay? Whose line integral is independent of the path chosen, whatever the 2 point you take, okay? It will be independent of the path chosen. It depends only on the initial and final points actually. When initial and final points are same, that we call that as closed line integral. So that is 0 for that special class of vector field, okay? But ordinarily, this will be depending on the path chosen, okay? Then you need to specify a path whenever you define this line integral, okay? I have a vector field, okay? I have a vector field. Let me write it as a F, okay? Some force field or something, okay? 3xy into I cap. 3xy into I cap. I cap means x cap. Minus y square into j cap. Y square into j cap. Okay, why it is mixed now? Actually, I just read some other question. Y cap. We have taken x cap, y cap here. So now, obviously, you can define a plane, am I right? This vector field is defined on a xy plane. You can see this one, isn't it? Let me take this one as origin 0, 0. Let me take this one as 1, this one as 2, this one as 3, okay? 1, 2, 3. 1, 2 and 3 somewhere, okay? So this is 0, 0, am I right? 0, 0. What is 1, 2? Tell me. X is 1, Y is 2. This is 1, 2. 1, 2. Is that okay? Now my initial point, I'm going to do line integral of this one, okay? Initial point is 0, 0, okay? My final point is 1, 2. Is that okay? My final point is 1, 2. I will choose 3 paths here, okay? I will choose 3 paths here. One is this path. I will go from here to here. Okay, then I will go from here to here. Is this diagram clear for you? Is that okay? I call this one as first one and this is second one. So this whole path from A to B, okay? Whole path from A to B, okay? I'm going to, call it as a first path, okay? First path. This whole path, I'm going to call it as a first path. Is that okay? Speak out. And that is the first path, okay? What is the second path I choose? Second path that I'm going to choose is straight line between A to B. Is that okay? Second path that I'm going to choose, that's a straight line between A to B. Can you just draw? So I call this one as a second path. Why? I call this one a second path, okay? Speak out. So let me do the line integral of a vector field along first path from A to B. Is that okay? A to B, A vector to B vector. So F bar dot DL bar. Is that okay? Speak out. Usually DL bar is written like this, am I right? DL bar is equal to dx into x cap plus dy into y cap plus dz into z cap. Okay, there is no z component over there here. But in the most general case, you have to take DL vector like this, isn't it? What is that F bar dot DL bar? Speak out. A to B. What is F bar dot DL bar? 3xy into x cap minus y square into y cap taken dot product with dx x cap plus dy y cap plus dz z cap. How do you deal with this z cap component? Speak out. Now you have to write 0 into z cap here. 0, that part is 0. I hope you can deal with it. Okay? Yes, that's equal to 3xy into dx. 3xy into dx. That's the integral A to B 3xy into dx minus y square into dy. X cap dot x cap, y cap dot y cap, isn't it? Now look at here, you got two variable, dx and dy. Okay, so different, isn't it? Now how do you do this one? How do you deal with this one? Look at here, this cannot be done unless you specify the path. This integral cannot be done unless you specify the path, okay? So that means this is like this, you are going from 0, 0 to 1, 2, okay? And you have to do the integral 3xy dx minus y square dy, okay? Unless you specify the path from 0, 0 to 1, 2, you can't do that integral, okay? Now I already specified the path. I have taken the first path from here to here. What is this point? 0, 0? 1, 0, this point. Is that okay? So this is first part of this first path, second part of the first path, okay? Let me take it like this. Now let me do that one. Now from 0, 0 to 1, 0, from here to here along straight line, okay? Now look at here. This is a line along x-axis, isn't it? Along this path, okay? This is the first path. Can I say this is a first path? First path. Let me write here. First part of the first total path, okay? So in that one, look at here. X is changing, okay? Dx exists, but y is not changing. Y is constant. What is the value of y here? Or you better to write that one, okay? In that first one, okay? You have chosen first path, okay? First part of the first path, okay? So that means, look at here, in that one, so x is varying from 0 to 1, am I right? Isn't it? But y is, what you call, dx exists, dx is non-zero. But y equal to 0, dy equal to 0. So can you just observe, when you move from this point to this point, y is not changing, y equal to 0, dy equal to 0, but x is variable. How x is varying? X is varying from 0 to 1. That's what I have drawn. You have to substitute these information into what you call this one actually. So that's why 0, 0 to 1, 0, okay? First part of the first path, okay? So that's equal to 3x into y, y equal to 0, isn't it? Y equal to 0, dx was non-zero, but still y equal to 0, that's equal to 0, isn't it? So not over, okay, not over. This total integral, so you are going from here to here, then here to here, isn't it? So this is one of the part. The next part is, what is the next part? Along first path, but second part of this path integral. So that means in that one, look at here, you are moving along y-axis, isn't it? You are moving along y-axis, okay? So that means again your x is not variable, x equal to 1, x equal to 1, dx equal to 0. If you move like this, am I right? X is not changing. So, but y is changing from 0 to 2, isn't it? dy is non-zero. dy is non-zero, but y is changing from 0 to 2, isn't it? Now substitute all of this information in this one, okay? Dx equal to 0, integral, okay? Integral, what was integral? T3 xy minus 3xy dx minus y square dy, am I right? This was the integral, am I right? Speak out. Now dx equal to 0, that's why this part is 0. You should just put all of this information. Minus y square dy minus y square dy. Is that okay? And y running from 0 to 2, look at it. This is a single variable integration. This is how it can be converted into single variable integration. It looks like it's a two variable integration, but after substitution of the information of that path, okay, this will convert it to single variable integration, that will be 0 to 2. Isn't it? Actually you have to write 1, 0, 1, 0 to 1, 2. Am I right? But how y is changing from 1, 0 to 1, 2 along straight line? Y is changing from 0 to 2, isn't it? Minus y square dy, that's equal to minus y cube by 3, upper limit minus lower limit. What is this one? Speak out. Minus 8 by 3. Is that okay? So that's why. So from what you call line integral from a to b, okay, from a to b along the first path, okay, or I have taken that first path here of f bar dot dl bar, that's equal to minus 8 by 3. Check that out. Any mistakes? You have to add these two, okay. So this is turns out to be 0, okay. So even though dx exists, okay, this is turns out to be 0, but this is non-zero. This is how you have to do. Can you do that one?
Sir, in first term, dy is 0. That's why we took it. This one is 0, sir. We start from the second term, the y square.
Y equal to 0. Both of the term contain y, am I right? That's why the whole integrand is 0 actually. Y was 0, okay, along this path. So solve some book problem, okay, you will understand this one, okay. Remember, the very similar situation we are going to encounter in case of complex analysis. Okay, there I am going to give any practice problem. You try to practice here itself. Is that okay? Very similar thing will come. Okay. Again, there we do the integration in a complex plane. Okay. Here this is a real plane actually. Everything is real values here. Is that okay? Or you do one thing. You take one more example, x into y here. Take x value here. Okay. X into y square. Take x into y square. I think that may not balance the dimension, but so take something, okay, x into y square or something. Then again, you may need to put that x value also, okay. X equal to 1, that is defined here, okay. X was not there. If x was there in this one, you have to substitute that x value here. Is that okay? Try to do the problems yourself, okay. Now, along first path, again, we got minus 8 by 3. We shall see what is the line integral along the second path, which is a straight line, okay. What is this one? A to B, but along second path, which is a straight line. So that is again 3xy minus y, 3xy dx minus y square dy. This was f bar dot dl bar, okay. Now look at here. Along straight line, how do you do? You should write the equation of this straight line. Because you have two variable integral here, okay. You have to convert that one into single variable. The whole idea is to convert that two variable integral into single variable integral and finding the limit of that single variable integral, okay. This is the whole essence of that method, okay. Now look at here. Along this straight line, can you write the equation for the straight line? What is the slope? Slope equal to 2, y equal to 2x. Is that okay? When y equal to 0, x equal to 0, or when x equal to 0, y equal to 0. When x equal to 1, y equal to 2. Am I right? That is the equation of this straight line. Okay. If you write y equal to 2x, okay, then dy is equal to 2 into dx, isn't it? So if x runs from 0 to 1, then y runs from 0 to 2. Am I right? If x runs from 0 to 1, y runs from 0 to 2, isn't it? Now just use this one to convert two variable integral into single variable integral. Okay, how do you do that one? You can just either convert that one into x variable or y variable. That's your choice. Okay, let me convert that one into y variable. Okay, integral a to b. Okay, integral a to b. 3. Wait a second. 3. Let me convert everything into x variable, okay, no, not y variable. 3 into x into, let me put y is equal to 2x again. Y equal to 2x, okay, into dx minus y square. What is y square? 4x square. 4x square into dy. What is dy? 2dx. 2dx, okay. Now look at here. I have converted the entire thing into x variable. Now, how does x varies? X is running from 0 to, when you go from point A to point B, x is varying from 0 to 1. Can you quickly do this one? Can you tell me what is this answer? Six into x square by 2 running from 0 to 1 minus, x cube by 3, am I right? 0 to 1 minus 4 into 2, 8, am I right? 8 x cube by 3 running from 0 to 1. Is the answer?
Minus 2 by 3.
6 by 3 minus 8 by 3. Minus 2 by 3. Now look at here, path integral depends on the path, isn't it? For first path, it was minus 8 by 3 or something. For second path, it is minus 2 by 3, it is different. Okay. Now look at here, I'll take the same vector field. I'll take now some other path. Let me define that one as a parabola. Is that okay? Let me take the same question. Let me rub out this. Quite difficult to draw on the top. Okay. 1, 2 here. 1, 2 here. Okay. 1, 2 here. X-axis, Y-axis. Okay. So 0, 0 to 1, 2. Let me take y equal to 2x square, a kind of parabola from here to here. Is that okay? What is the equation? Y is equal to 2x square. Okay. You do the line integral from A to B along this path. Some curved path. I have given the equation of the curve. Then how do you do? Now, using this y equal to 2x, so convert this two variable integration into single variable integration. Define dy, isn't it? What is dy here? Dy is equal to 2 into 2x dx, isn't it? And just using that one, substitute that one. Y will vary from 0 to 2, isn't it? Or x will vary from 0 to 1. Either convert that one into x variable or y variable. Is that okay? Speak out. So y is equal to 2x square. Substitute these two, okay, into this equation and convert that one into single variable integration. Okay, that's how we do. Any path integral, okay, if it is horizontal and vertical, it is very easy, am I right? Along horizontal direction, dy equal to 0, okay. Along vertical direction, dx equal to 0. You can substitute respective value, you can do. If there is any curved path, you should write again. If you know the equation of that curved path, okay, then you can use that equation to convert two variable integration into single variable integration. Okay, this is two-dimensional path integral actually. Okay, you should be able to imagine 3 dimension and you should be able to do that one. There are a couple of questions in the Griffiths. Do that one. Let me give one more question here. So try it out after the class. I have a vector field A, okay? So try this out after the class. Y minus 2x into x cap plus I plus 3x minus 3x plus 2y into y cap. 3x plus 2y into y cap. Okay? So compute the circulation, okay? Look at here. I defined that one as a circulation. What do you mean by circulation? Closed line integral. Compute the circulation about a circle C in the xy plane centered at the origin, radius 2. It's very difficult, okay? Drawing these coordinates, then drawing the circle is difficult. What you have to do? First draw the circle.
What the question?
Compute the circulation, write down. Compute the circulation of this vector field. Compute the circulation of this vector field about a circle C. About a circle C in xy plane. About a circle C in xy plane. Centered at what you call origin. That circle is centered at origin. Is that okay? And it has a radius 2, 1 and 2 here. Is that okay? X-axis, Y-axis, okay? And that traverse in the positive direction. See, traverse in the positive direction. What do you mean by that? Take this direction and do that one, okay? Usually anti-clockwise is, he said traverse, there are, once you have a closed line integral, whether you have to take like this or like this, clockwise or anti-clockwise, am I right? That's the question, am I right? He's writing traverse in the positive direction, you take it as an anti-clockwise direction. So take that one. No. I think this is positive that he may be saying. Anyway, just do that one. Check that out. Take it this is anti-clockwise, am I right? Yeah. I mean, if you take an angular part, so this is actually anti-clockwise thing is increasing direction of angle actually in case of polar coordinate. If you define angle theta like this, okay? So anyway, so it doesn't matter. You just do that one. Is that okay? So take this one as a, so this is radius 2, okay, centered at the origin 0, 0. No, some other question. I mean, you have to solve Griffith's question as a homework. Let me mention that one, okay. I have defined this what you call path, okay, this is a closed path, okay, that closed path integral is called as circulation, okay. Look at the question, you have given a vector field, compute the circulation of a vector field about a circle. Look at here, this is what I have drawn, okay, but in the question they didn't draw that one, okay, that you have to draw. Compute the circulation of a vector field, okay, about a circle in a xy plane centered at 0, okay, and what you call radius is equal to 2, and take that what you call path integral anticlockwise. Now suppose if I give some vector field, okay, just think over it, okay, I'll give one vector field, okay, f is equal to x minus 3y x cap, okay, y minus 2x. Do it later after I interpret the Stokes theorem. X minus 3y x cap, y minus 2x y cap, okay. Now seize the closed curve in xy plane, which is a kind of ellipse, where I will define major axis, minor axis, A, B I will provide, okay. Then how do you do that one, okay? Let me mention that one. How do you do that one?
Sir, we can write the equation of ellipse.
What equation?
And then
X square by a square plus y square by b square? Yeah, so that's one way. Is there any other better way that you can think of? For earlier question also, okay? For earlier question also, you had a circle, am I right? Look at here. This will happen. If you draw the coordinate, then draw the circle. Draw the circle, okay? Then draw the coordinate. Why it should come 0? For only conservative field it will be 0. It will not be 0 for all field. No. Don't think further, okay? Don't think further. Do the problem. Just do the problem, because I am giving it as a practice problem. You need to practice, okay? You need to have practice of that, what do you call, taking that that one, okay? Wait a second.
sir, by converting it into polar coordinate.
Polar coordinate, that is, I think, more easier, isn't it?
Yes, sir.
In case of circle, if you convert that one into polar coordinate, I think that may be more easier, isn't it? So this is how you generate the idea, okay? Now look at here. What you can do is you have something. What was the vector field I have given? Some earlier.
Y minus
2x x cap 3x plus 2y y cap, isn't it? So this was the vector field I have given. Am I right? You need to find the what you call circulation here. You will end up with that a bar dot dl bar. Okay, what is this a bar dot dl bar? So that will be y minus 2x into dx plus 3x minus 3x plus 2y into dy, isn't it? You will end up with this one, isn't it? Then you need to do integration. What you can do is you can use parametric equation. We call that one as a parametric equation. Am I right? What you can do is x equal to, what is the radius? 2 cos theta. Y is equal to 2 sin theta. Am I right? Is this a parametric equation?
Yes, sir.
X equal to 2 cos theta. Y equal to 2 sin theta. If you take this one as theta, this is 2. Okay. X coordinate is 2 cos theta. Y coordinate is 2 sin theta. Okay. When you run this point throughout this one, theta will run from 0 to 2 pi. Substitute this one. It will be automatically converted into theta variable. Dx also you can write in terms of d theta. Dy also you can write in terms of d theta. That's another way of doing that one, okay? One thing is you can use the equation of a circle, x square plus y square is equal to 2 square, and you can convert this two variable into single variable using this equation, okay? Other one is using the parametric equation. Why I called parametric equation? Here also you can find the parametric equation, isn't it? And you should know how theta runs, okay? Because I have taken circulation here, okay? Theta will be 0 to 2 phi. You should know the range of theta. Is that okay? That's the best way to do that one. Otherwise, if you use this one, how do you do, if you use this equation, how do you do that one? If you go from here to here, y will be 0 to 2, am I right? If you go from here to here, y will be 2 to 0. Like that, I think you may need to split the integral, isn't it? That would be more lengthy, am I right? Suppose if you want to do in Cartesian coordinate only, without using parametric equation, try in both way. Okay, now look at here. Don't be lazy in trying different ways, okay? If one method is lengthy, you will remember that it is lengthy, this is easier, and you are going to apply that one later. I get your point. So in the book, sometimes some problems may be lengthy, okay? Later when you apply some theorem and all, that problem will be very easy to solve, okay? But you should do in both way. If you do that one, then you will remember that this is lengthy, this is the easiest way, and you will follow the easiest way, okay? Unless you experience that one, you don't follow the easiest way. Is that okay? I get your point. So that's why do in both way. Do in Cartesian coordinate as well as this using parametric equation. And here also you can define what you call, I think, parametric equation. I hope so, isn't it? How do you write parametric equation here? X equal to a cos theta, y equal to b sin theta, so that x square by a square plus y square by b square is equal to 1. That is the equation of this ellipse, isn't it? Is that okay? But in the question, he has given parametric equation also, okay? So I was just checking whether you know this idea or not, okay? In the question, he defined parametric equation. But in some other question, he may define ellipse with major axis, minor axis, isn't it? And he may ask you to do the, what you call, circulation, isn't it? Now look at you, he has given along the curve x equal to 2 cos t, y is equal to 3 sin t, y equal to 3 sin t from t is equal to 0 to 2 phi anti-clockwise. Whatever positive he is talking about, that is anti-clockwise only, okay? Along anti-clockwise direction. Take anti-clockwise. Take anti-clockwise. Answer is 6 pi. Okay, earlier question answer was, that was also anti-clockwise. Answer is 8 pi, okay? This answer 8 pi. Note down the answer. Try to do these two questions later, okay? So there are much more questions to be practiced. We shall see the what you call exam questions. Then we can collect the question from the book, okay? Surface integral. We have already taken this one, okay? Isn't it? If we have the surface, okay? If we have the surface and we have vector field, okay? We have the vector field in space. We have the surface. What we do is, again, in case of surface integral, okay, or it's a kind of flux, whatever the, again, I call that one as a flux, am I right? Calculating the flux through this surface, am I right? What we do, we are going to divide our, what you call, surface into small patch of areas, am I right? And we are going to define area vector. There are two choices of area vector. Okay, we choose one of them. In case of open surface, this is an open surface, am I right? This is an open surface. So then dA vector, you can choose like this or opposite also. And again, you have to take this kind of patch of area at each and every point on this surface, and you have to take dot product of that area vector with a vector field. Is that okay? Vector field dot dA, okay? and then you have to integrate that dot product over the surface. Open surface integral. There is no closed symbol here. Okay. We call this as flux of vector field V, isn't it? Flux through the surface S or like that, isn't it? Flux of the vector field through the surface S. But look at here. Again, this dA vector is your choice. Okay. Here. You can choose either dA vectors like this. Okay. Suppose if you take somewhere here, okay, you can take dA vector like this. Okay. Or you can just invert all of those dA vectors. Okay. That's your choice. If you invert all dA vector, then you will get flux which is negative to earlier flux, but magnitude will be the same. Magnitude of the flux will be the same. Okay. We call this as flux of vector field, isn't it? We have already taken this one, or we can call it as a surface integral of a vector field. Okay. Surface integral of a vector field. Suppose if our surface is a closed surface. Okay. Should give some shading. Isn't it? Closed surface. Okay. And you have a vector field. Okay. Okay. You have a vector field in space. I have taken constant vector field, whatever. Okay. You have a vector field in space. I should not have taken constant vector field, isn't it? I have a closed surface, okay, and I have a vector field. You may have what you call net outward flux, or you may not. That doesn't matter, okay. But this is a closed surface, okay. This was an open surface, okay. For closed surface, again, we can define what you call area vector. We can have one idea, isn't it? Here you can't have what you call, you can't define the direction at all, isn't it? Here. What would you call this one? Outward, inward, nothing. But here you have outward and inward from the region, am I right? This closed surface, okay, that will form a volume V, isn't it? That will form a volume V, that closed surface. And what we do is, again, we are going to define closed surface integral of a vector field, okay? In that case, what we do is we choose dA vector outward from the region everywhere. Okay, we choose dA vector outward from the region of this volume. Okay, this closed surface will constitute a volume, and you can define dA vector like this, and you can take a dot product of dA vector with this what you call vector field at each and every point on the surface. Okay. At each and every point on the surface, okay, you can define an elementary area, and you can take a dot product of vector field at that point, vector field at that point with that elementary area, and you can integrate those dot product, okay, and we call it as closed surface integral, okay, closed surface integral. Now, usually, whenever you define the surface integral, okay.
Here, sir, I mean, V and dA will be in parallel direction, right? I mean,
Need not be. I have taken one example of this. Need not be. Where I have taken? Why? It always should be. Why it should be? This is a definition of closed surface integral. Vector field, you can take any vector field. I am not saying what is the vector field here. Symbolically, I have drawn, these are the vector field like this, okay? Symbolically, I have drawn some vector field there, okay? Now look at here, what we do is, again, this is a convention, okay? This choosing dA in this direction, this is a convention to make this outward flux positive, that's it. This is also flux, am I right? You can talk about outward flux, am I right? If vector field lines are going outward, okay, we, again, whatever the flux we calculate, we should get positive. That's why we have chosen that dA vector like that, okay? That's always convention. There is no other, what you call, logic for that one, okay? Other than the convention. To make outward flux positive, we choose dA vector like this, okay? To make outward flux positive, inward flux negative. I think I did explain that one in the previous class, isn't it? Check that out. Now, the next thing is, look at here again. Yeah, I just forgot to mention one thing. So this is the surface S. Okay, we have taken V bar dot dA bar over the surface. Am I right? We call it as flux through the surfaces and all, isn't it? Usually this surface integral, okay, surface integral of a vector field, you should define a surface first. Am I right? For that surface integral, to calculate surface integral, you need to define the proper surface. Am I right? Either open surface integral or closed surface integral. You need to define the proper surface. Am I right? Without defining a proper surface, can you do this integral? No, isn't it? Just like in case of line integral, isn't it? Line integral from one point in space to other point in space, you need to define a path, isn't it? To do that line integral. Similarly, you need to define a surface properly to do the surface integral, isn't it? But there are some special class of vector field, okay, whose surface integral is independent of the surface chosen. They depend only on the boundary line of the surfaces. Boundary line is a kind of closed path. Can you see this one? Boundary line of, so take open surface integral, okay? Usually surface integral depends on the surface chosen. If you choose different surface. So what I do is I will take a boundary, okay? I will take a boundary here. So let me choose that boundary as a circle. That is more easy, okay? I'll choose this one. I will take a plane of this circle itself. That is one of the possible surface. Can I write it as S1? Now I will take this circle as a neck of some pot. This pot is like this, okay? I will take this circle as a neck of some pot. Is that okay? Then I'll call that one as that pot as a surface S2, isn't it? So if you take different surface, look at here, this surface integral may be different, am I right, in the most general case. Speak out. But there are some special class of vector field. Once you, again, what we do is this circle, whatever I have drawn, this closed line, we call this a boundary of S1, boundary of S2. For an open surface, we define a boundary. That boundary is a closed path actually. Whatever the open surface you take, okay? Whatever the open surface you take, is that okay? Suppose something like this, okay? So the boundary line will be a closed path. Can you just imagine this one? Speak out. Suppose you take a hemisphere. Hemisphere is a, what you call, surface, am I right? Curved surface. Boundary of that surface is a closed path actually. Is that okay? Or take a square shaped surface, okay? So planar surface. What is the boundary of that surface? That is a closed path. Isn't it? Is that okay? That's a closed path, am I right? Speak up. That's a closed line, isn't it? Boundary of an open surface is a closed line. Can you imagine this one or not? Quickly tell me.
If I take one balloon shape.
Again, this what again take it as a pot. Look at here. Now what I do is I have a circle, okay, circular path, okay, circular path. Now what I do is I am going to define one surface S1, okay. This circular path is a boundary for this surface S1, which is a plane, okay. Now that circular path, again using that circular path, I am going to do what you call define a part. Is that okay? Where this circular path is a neck. Now for this surface S2, okay, which is a what you call your part, okay. This surface S2, for this surface S2 also, this circular path is a what you call boundary line, isn't it? Speak out. Can you imagine? Because part is also open surface, it is not fully closed, isn't it? So if you have a what you call plane, okay, square shaped plane, okay, so this is a what you call boundary line, okay. Can you just imagine? Is that okay? You have a plane, so this is the boundary of the plane. Can you imagine that one? You have a hemisphere, okay. you have hemisphere. Is that okay? You have a hemisphere. So, but boundary of that surface, so that's a circle, isn't it? Is that okay? That's why boundary of any open surface is a closed path, okay? Is that okay? Boundary of any open surface is a closed path. Either you take a pot, okay? What is the boundary? You don't have boundary anywhere. These are all closed surfaces. You have boundary only here, am I right? Boundary of that one. That means your surface end over there, am I right? Your surface end over there. Your surface end over there. That's what I call that one as a boundary, okay? Now, once I have chosen this boundary, okay? With the same boundary, I can define many surfaces just like I did here. With the same boundary, so why can't I define what you call cubical surface here, isn't it? Isn't it? With the same boundary. Is that okay? Just like a box which is, so put like this. Is that okay? With the same boundary. Now look at here. What I'm saying is, once you fix the boundary, so if you take a different surface, usually this surface integral should be different for different surface chosen, isn't it? Are you getting point? For a given boundary of the surface, okay, if you choose different surface, your surface integral, ordinarily, it should depend on the surface chosen, isn't it? But there are special class of vector field, okay? Your magnetic field is one of the example. There are special class of the vector field, okay, whose surface integral is independent of the surface chosen for a given boundary. Is that okay? For a given boundary, surface integral is independent of the surface chosen. Suppose if you take here, so again let me choose this surface S1 and surface S2 for that special class of the vector field, whatever I told. Okay, surface integral is same for both of the surface. That's a strange class of vector field. Is that okay? For that kind of vector field, closed surface integral is 0. For that special class of vector field, for which surface integral is independent of the surface chosen, depending only on the boundary line of the surface, okay? For those class of vector field, closed surface integral is 0. And we need to learn much more about that class of vector field. Speak out. Magnetic field is example. Is it okay? Magnetic field is the example.
Sir, is there any name of these vector fields?
I think there are some names, okay? I think you said solenoidal, like that, isn't it? I think there are some names. We shall see that one. It is there, okay? We need to define much more theorem, okay? I hope you can imagine what is the boundary of an open surface, which is a closed path actually, okay? Just try to imagine that one, try to draw that one. These ideas are required, okay? Now let me quickly give, yeah.
Can you say once again, I am writing
Which one?
statement, sir, whatever you say.
There are special class of vector field. There are special class of vector field for which surface integral is independent of the surface chosen for a given boundary line. Is independent of the surface chosen for a given boundary line. Don't choose one surface here, other surface here, not like that, okay? So take one boundary first, then try to define different surface.
If I squeeze the surface,
If you squeeze the surface, that will become what you call closed surface.
if I squeeze the boundary line,
It will become closed surface.
then it will close surface.
If you squeeze that boundary line, it will become closed surface, just like a balloon. You told about balloon, am I right? After you blow that one, you are going to squeeze that one and you are going to tie that one, am I right? That will become a closed surface. So take it as again, initially balloon, you suppose if you are not blowing that one, it has an open neck, am I right? It's an open surface. That neck, that is little folded, am I right? You can think that one as a boundary line of the surface. Once you blow and then you are going to tie, am I right? You are going to squeeze that one. Yes, that's a closed surface.
Then this, whatever the boundary, then boundary will be,
Zero. I mean, there is no boundary at all. For what you call, for this closed surface, there is no boundary. Just move on. You will not end anywhere. You will come other side, isn't it? But here, if you move on, you will end up somewhere. Am I right? There is no more surface somewhere. That's a boundary. Closed surface will not have any boundary, isn't it? Speak out. Now, let me quickly give you some idea, okay, regarding how to take the surface integral, okay? Let me take some other example so that you can solve Griffith's examples yourself, okay? Yes, again, let me explain this one, then we shall close the session, okay? I'll take one vector field, okay? F is equal to 4xz into I cap, x cap, minus y square, y cap, okay? Plus yz, z cap. Is that okay? So now my surface is, I'm going to draw the cube first, okay? My surface is a cube, okay? Surface of a cube. Let me just explain the method here, okay? X, Y, Z. Let me just explain the method. You should do it yourself. This is the origin, okay? This is 1, this is 1, this is also 1. Is that okay? Now you have a vector field which is in the space, okay? Look at it. It depends on x, y, z, okay? It has a different direction at different point in space, okay? Now you need to find the what you call surface integral. You can go for closed surface integral or open surface. Let me go for closed surface integral. If you know how to find the closed surface integral, you should know. I mean, you will find how to find the what you call open surface integral also, okay? So there is a Griffith's problem where what he has taken is it is open below here. So this is a boundary. It is open below. It is closed above. Okay, just like so it is like this. Okay, can you imagine like this? This is open. It is like this. So can you just imagine this one? Like this. This is open here, okay? Which one? These are the surfaces. So that is this surface. This is this surface, okay? Like this, okay? So this is open here, okay? That's what Griffiths mentioned, one of that one, okay? Once you mention open surface integral, now you should know what is the direction of the surface that you need to choose, whether a surface area, okay? So this is one planar surface, whether dA should be chosen like this or inward, am I right? So dA should be chosen like this or inward, isn't it? So that's the question, okay? So that he has given everything, all hint, try to solve it. So let me solve this problem. Let me take closed surface integral. I'll put a closed thing here, okay? I'll just put it like this. Let me take a closed surface integral. Is that okay? Let me close this one. Let me take a closed surface integral of this vector field throughout this one. Once I define closed surface integral, I know what is my dA vector. I know what is the dA vector direction. That is this one, am I right? I know the dA vector direction here. What is this one? Here, isn't it? I know the dA vector direction, isn't it? Once it is closed. That is here, isn't it? Speak out. Once I know that it is closed surface, okay, I know what is its dA vector direction, okay. Now suppose if you want to do, again, now this surface integral of this vector field, okay, surface integral, closed surface integral of this vector field f bar dot dA bar, okay, you need to divide the surface into different parts because you have different planes. Total 6 planes you have, am I right? 6 square shaped planes you have. You have to divide that one into 6 parts. You have to divide that surface integral into 6 parts, okay. Let me just explain some of them, okay. Suppose if you take this top surface, okay, this top surface, this top surface, okay. Again, you have to write the dA vector. Once you write the dA vector, then you can take the dot product. After taking dot product, you should know what is the range of what you call this variable, isn't it? That's it. You can do the integration. Now let me do for this top surface, okay. What is this top surface? If you take a dA vector here, okay. If you take a dA vector here, now actually I have shown that one as a what you call circle. You can take it as a square also, okay. On a plane, you can define a what you call elementary area. I mean, if you are dealing with a Cartesian coordinate, you better to define your elementary area like this, okay. dA. Suppose it is x, this is y. Then this dA you can write as dx into dy. Dx here, dy here. You can write dA is equal to magnitude of dA. That's equal to dx into dy. Is that okay? If you define any what you call infinitesimal area on xy plane or parallel to xy plane. Can you imagine parallel to xy plane? If you define an infinitesimal area on a plane which is xy plane or on a plane which is parallel to xy plane, okay, then you better to define that infinitesimal area as a square, infinitely small square, okay, and that what you call magnitude of that one is dx into dy itself. Is that okay? Now look at here. Here also I do the same thing. I am going to take elementary area here. Is that okay? Which is a square shaped. Now this plane is parallel to xy plane, isn't it? Okay. So that's why this area vector direction I know. What is the direction? dA vector. Direction I know. That's along z cap. Am I right? What is its magnitude? That magnitude is equal to dx into dy. That means if you move along this plane, z is not changing. Z equal to 1 only. X and y are changing. That's how dx and dy will come in your integration. Is that okay? Then what you have to do? You have to take dot product with f. Am I right? So again, if you take dot product with z cap, only z part will remain. Am I right? So that integral will be yz into dx into dy. Okay, over this surface I am doing this surface integral. Okay, dx into dy. Is that okay? Z cap dot z cap. That's what I have taken. Now, what is z value over this surface? You should know. You should have the 3-dimensional imagination. What is z value? Z equal to 1. Am I right? You should put z equal to 1. How y and x are changing? Again, this is actually double integral. Okay, we don't draw that double integral. Okay, we draw only single integral. But when two variable comes here, then take double integral. Okay. Earlier one was not double integral. Okay, line integral was not double integral actually. You had a plus in between. Okay, but you have dx into dy. Okay, this is a double integration. Now in that double integration, you should specify both x and y what you call variable. Okay, now look at it. If you take this square, okay, so your x is running from 0 to 1, y is also running from 0 to 1, isn't it?
We can say that it is in xy plane.
Parallel to xy plane.
Parallel to xy plane, z equal to 1 constant.
Z equal to 1 throughout this plane, isn't it? Z equal to 1 throughout this, because this plane is perpendicular to z axis.
If I will put one middle of this, square, one plane.
That will be z equal to half or something. Now look at here. What I am saying is you should know the range of x and y that's equal to 0 to 1, 0 to 1. along this square, okay, x is 0 here on z axis, x equal to 1 here, y equal to 0 here, y equal to 1 here, am I right? To sweep this region, okay, you have to take this range of the integral. Is that okay? Let me give you much more challenges, okay? Try to do that one. So similarly, if you take this one, here also your dA vector is dx into dy, okay? dA vector, that's equal to dx into dy, okay, because this is also parallel to xy plane. But what is dA vector direction? That is minus z cap. If this is z cap, look at here it is minus z cap. Is that okay? Again, x and y vary from 0 to 1, 0 to 1. Is that okay? So like that, if you take dA vector here, what is the dA vector direction? Y cap, am I right? What are the variables here? Yeah, its direction is y cap. Now look at here, this plane is parallel to xz plane. Can you imagine? So that's why in the xz plane you have to write, or in any plane parallel to xz plane, you have to write dA vector as what you call dx into dz. This is dx. Okay, this is dz. Dx, dz, y cap. Okay, use this logic to define area vector throughout the, over all what you call 6 different planes, and take a dot product with f and integrate. I think everywhere your x and y or z, okay, those are varying from 0 to 1, 0 to 1, 0 to 1 only, am I right? Whatever the phase you take, am I right? Here also 0 to 1, yeah, variables will be 0 to 1 only, okay? Do this problem. Wait a second, let me give you the answer also so that you can match. Wait a second. Let me give you the answer of that integral, total integral 3 by 2. 1, 2, 3, 4, 5, 6. Yeah, he has taken 6 phases. So answer is 3 by 2. Okay, check this out.
Sir?
Yes.
Sir, here we also use the concept of a single variable, sir. So we have to convert this one to single variable, sir. Double integral, sir.
No. You can't directly convert into single variable, okay, unless you have the surface equation. Even though you have surface equation, I think you can't convert, okay. You have to deal with the double integral. We shall see that one. In case of volume integral, you will have much more experience, okay. How to deal with the double integral. Here it is a square, that's why it is 0 to 1, 0 to 1, 0 to 1, am I right? Where 1 is the side of the square. It's quite easy, okay. If it is a triangle, then how do you run the integral limit? Okay, multiple integral, okay, over a triangle. How do you run the limit? Okay, that will come in the what you call this volume integral actually. First, try this volume integral. Try to grab the logic. Let me explain in the evening. Okay, try to grab the logic yourself. Okay, or let me. I don't think he defined any other questions. Designed any other questions. Wait a second. Integral over a bottom of a box. Okay. Integral over a tetrahedron. Yeah, here's volume integral over a tetrahedron, not surface integral. Now let me try to grab the surface integral over a kind of prism shaped surface or something, some other kind of surface. Again, Cartesian coordinate should be used. There are some other surface integral where you can go for spherical polar coordinate and all, where it is more easy. Okay. So, but let me try to grab some question, okay, so that again that double integral was very simple here, okay, 0 to 1, 0 to 1. But let me try to give the problem so that you should think on the double integral, how to run that double integral, okay, that also you should learn, okay. So now the last part is volume integral. Volume integral. Volume integral of a scalar actually, okay. If I have a scalar field, okay, I can define a volume V, okay. I can define a volume V. I can define a volume element. Suppose I have some volume, okay. I can define a volume element, am I right? D tau. And I can multiply my, okay, I can multiply my vector article. I can multiply my scalar field at that point with that volume element, and I can integrate throughout the volume. This is the total volume. Is that okay? So that's the meaning of volume integral. Okay, scalar field multiplied with volume element, infinitesimal volume element, and integration. Okay, and in Cartesian coordinate, this d tau is equal to dx into dy into dz. Now let me give the simple question. Wait a second. Is that okay? Now let me give the one of the example here. So you can take volume integral of vector field also. Okay, v vector dot d tau. In that case, what you need to do is you have to do vx into d tau integral, okay, into x cap plus vy into d tau integral, okay, into y cap plus z component. You have to do like that. You can do the volume integral of vector field also, but I don't think we use that one much, okay. But volume integral of scalar field, that is quite frequent for us, okay. Now look at here, let me give you one simple example, okay. How does this volume integral works actually? Let me take some scalar field, okay, and let me integrate over a cubical region, okay. X, Y, Z here, okay. Let me integrate over a cubical region. This is the origin. Now suppose this cube is of side A. Let me take A here. Is that okay? Cube is of side A. Now, again, if you take any volume element inside that cube, and again that volume element, that this d tau is dx into dy into dz, you can take like that. If you take a small volume like this here, okay, whose width, height and breadth will be dx, dy, dz like that. Is that okay? And again, you can multiply that one with some scalar field that I have defined, suppose x, y, z, and you can integrate, isn't it? Suppose, for example, the scalar field can be some x, y, z square, okay? This is equal to x into y into z square, okay? Then how do you do this volume integral? Volume integral of what you call x, y, z square into d tau. What is d tau? dx, dy, dz, isn't it? Actually, it's a triple integral, but we write only one integral symbol, okay? So after writing these things, you have to write three integral. Now, how do you take x, y, z range? You can do this integral in any order, okay? You can do the triple integral in any order. Mathematics allows that one, okay? But what are the ranges of each of these x, y, and z? Tell me. What are the ranges of x, y, z? You have to run this d tau throughout this volume, am I right? How do you run x? How do you run y? How do you run z? Integral with respect to dy, dz, dx, dy, dz, am I right? What is the range of x you take? What is the range of y you take? What is the range of z you take? Quickly tell me.
Sir, 0 to A, sir.
0 to A, 0 to A, 0 to A. That will cover the region of the cube, isn't it? Think over it, okay? It is 0 to A, 0 to A, 0 to A, okay? Very simple. Now what I do is, okay, I will give you one more volume region, okay? I'll give you one more volume region like this, suppose. I'll give you one more volume, wait a second, which is a prism shaped, can you just imagine this one? This is also A, this is also A, you will take this also A. That means this is cut like this diagonally, suppose. Cut into piece, okay? Now I'll take the same scalar field, and I need an integral over this volume. Then what will you do? No, I cut that one. Then how do you run the limit? You just tell me how. I mean, there is no need to take dot product these things here, isn't it? Just writing just x, y, z square, okay? dx, dy, dz, am I right? Now how do you run x, y, z here in this kind of shaped volume region?
Sir, we need to know the equation of this plane, sir.
Yes, we need to know the equation of the plane, or you need to know the equation of this line. Okay. Now try to do this one. Think over it. Is that okay? How to do this one? So try to have the imagination how this integral is done actually. Okay? How this integral happens. Okay? Yeah. Let us discuss this one then. Okay?
The line.
You have to, again, you should know how this integral works. Okay? First you do in one of the dimension, am I right, along x-axis. If you do the integral, you will get a line kind of thing, am I right? Then you take that answer and you do the integral along y-axis. You will get an area kind of thing, am I right? Then you make it as a volume, isn't it? That idea you need, and from that idea, so try to solve that volume integral. Let me give the hint in the evening. Okay, I'll give the hint only. Okay, because I need to discuss that Stokes theorem and Gauss theorem in the evening, so that slowly we can go to other part tomorrow. Okay, so shall I close this class? Yes, speak out.
Sir, can you please once explain in this second figure, last figure, sir, why we are not running 0 to 8, sir?
Because if you run 0 to a, 0 to a, 0 to a, that will become a cube, not this shape. This is not a cube.
Okay, sir.
Isn't it? How can you run the same limit here and here?
Not possible.
Isn't it? Not possible. Suppose your vector field is constant, okay? If your vector field is constant throughout the region, then what you can do is, you can find the vector field, volume integral here, you can cut down by 2. But your vector field have different value, okay? At different point. That's why here you will get different volume integral, here you will get different volume integral, okay?
Whatever you say, in this regular set cube.
Suppose if you want to just take volume, what do you mean by volume? You can take this one as 1, then this will again, if there is nothing, this is a volume, am I right? 1 into d2. So that means 1, you have taken everywhere 1, am I right? In that case, you can find the volume of this one, divide by 2, you will get volume of this one. That's quite simple, okay? But you have a scalar field which takes different value in different space. That's why you should know how to run the integral. So do that one. Let me give the hint later, okay? I think you can solve this problem. 1.26, I think 1.27, 1.28 also. Example, couple of example. Example 1.8, this is similar to this one, okay? And problem number 1.29, I think 1.30 also can be done, 1.31 can also be done, okay? And 2 more problems that I mentioned on the board, okay?